Welcome back. I hope you enjoyed your lunch. So the toughest slot to talk is always right after lunch. And for this purpose, we've selected an excellent speaker, Professor Tom van Cutsem from the Department of Computer Science from the group DistriNet. And Tom will give you an update on blockchain and distributed ledgers.
All right. Thank you, Bart, for the introduction. So, hello, everyone. My name is Tom, and indeed, let me try to keep you awake in the hour after lunch. Let's try and make it informative. So my talk is going to be an introduction, a refresh to blockchain and distributed ledger technology. And what I actually want to do, let's see if this works. Okay, if I get close enough, it works. So what do I want to cover with you today? So first, we're actually going to go back to the origins of blockchain. Well, maybe not the real origins, that would take us back too much, but really sort of look at the birth of the first blockchain, which is Bitcoin, have a look at how that came to be and what problem they tried to solve. Then we'll look at a little bit under the hood at the cryptographic building blocks, but certainly not in the same depth as you will see in other courses, really just to get a sense of what are the basic building blocks on which this whole system rests. Then we'll have a look at the systems aspects of blockchain, looking at the life of a blockchain transaction, like what does it take for a blockchain to process transactions. And then we'll look at probably the core algorithm of most blockchains, which is the consensus algorithm. I'll talk about that in a minute. And we'll wrap it up also with a look at enterprise blockchain and how it's different from the public blockchains that most of you will have heard of, like Bitcoin, Ethereum, and so on. We'll compare and contrast those. If I have time left, I'm not sure, but we'll see. If I have time left, I can say a few words about smart contracts. And then I'll point out some of the latest trends and current research in the field at the very end. Okay, so let's start with the origins of this whole thing. So the origin of Bitcoin can be traced back to the wish to create electronic versions of money, or e-cash, if you will. And in particular, well, you might think, well, what's digital money? We have it, right? Like we do electronic payments all the time. Well, that's true, but in all traditional systems of money transfer, like you think about bank transactions or you think about credit card transactions, there's always this central party in the middle that is doing all the bookkeeping, right? And cryptographers, and in particular a group called the cypherpunks, so these were people with the rise of the internet, they were really looking at, okay, just like the internet is a decentralized network, there is no single node that has control, can we build systems of money transfer that have no single point of control or a single point of failure, right? And the thing is, if you think about cash, if I pay you money for my coffee and you take my dollar bill, we don't need to appeal to a third party. Of course, in some sense, yes, we both trust the government that has issued the money note, of course. But other than that, our transaction is completely anonymous. I don't need to reveal my identity to the buyer, and there's no trace of that payment left, okay? So that's the privacy you get with traditional cash payments, and you don't have that with the digital systems. So the question is, can you do digital payments that are anonymous and untraceable? That's sort of the origin story. What we got is not anonymous and untraceable, quite the contrary, but I'll get to that later. One of the people that was very instrumental in those early days is David Chaum, cryptographer. He created a company called DigiCash, and that was actually based on one of his inventions called blind signatures, which is an idea where you can have an authority sign a document without the authority knowing the details of what they sign. So the root problem that the cryptographers had to deal with is actually very similar to something Bart mentioned in his talk about the timestamping problem, when he talked about digital certificates and revocation, and then the certificates minted afterwards no longer being valid. So you have a similar problem with digital cash, which is the following. Let's say Alice wants to send digital money to Bob, and what she can do is she can sort of create a note saying, I hereby declare that I transfer one of my digital tokens or coins to Bob, and you just sign that with the traditional public key crypto system. There's nothing special about that. You just use digital signatures, and then you transmit that over the network, and then Bob has that node, and they can show that node to anyone to show like, hey, I got a coin from Alice. The problem is, what stops Alice from creating just another transaction object where she says, I'm going to transfer that same digital token, I'm going to transfer that to Carol, and I'm going to sign that as well. And now you send that over the network, and Carol has this note saying, hey, I got this letter from Alice saying I got her coin, okay? And now, of course, the troubles begin when Bob and Carol later make those payments. It turns out that who actually has the money, Bob or Carol, right? So clearly, one of those two nodes has to be declared invalid, depending on what node came first. So that's the timestamping problem, right? You have to all the parties in the system have to agree on what came first. So that's the key problem. How can Bob and Carol be sure that they are actually the exclusive owner of the coin? So the most straightforward solution, which is also the solution that we use in most of our payment systems today, is to introduce what's called a clearinghouse. And the clearinghouse in a payment system, one of the roles it plays is indeed to make sure that the nodes that are being presented are valid, and they can be, as a central party, it's very easy for them to just keep a record of what node came first, and therefore be the party that dictates what is the order of transactions. Therefore, that second node will, the second node that is presented to the clearinghouse can be deemed invalid. Okay. Now notice that, and this was the big breakthrough, I think, that Chom did with DigiCash and blind signatures, is that the big problem with this is that this one clearinghouse can see everything. That's like terrible, right? Like you have Big Brother seeing all the transactions. What they did with blind signatures is that you could actually create a clearinghouse that you could still guarantee that no node could be spent twice without the clearinghouse actually being able to observe who is paying whom how much. Okay, so this anonymity, that was already there, but in DigiCash, for instance, they had that central clearinghouse. And that brings many different risks. So you heard Professor Beesens talk about risks in the course just before lunch. What kind of risks? Well, certainly technical risks, like clearly there's an availability issue. What if your clearinghouse goes down, then all payments stop. And I think, well, these days it's less common, but I remember the days when on Christmas, when you went shopping and the payment terminal wouldn't work. And that was like, when there's an outage in the payment system, it has a dramatic effect on everyone. So there's that. There's the security risk, of course. If hackers can get into the clearinghouse, then obviously they can do tremendous damage. But there's also more subtle risks, economic and political risks. For instance, what if the company that is running that clearinghouse goes bankrupt or is threatened in court if there's litigation to that company? This is actually what happened in the DigiCash case. They went bankrupt in 1998, and with the disappearance of that company, like literally all the money you had in the system was worthless, right, one day to the next. So enter blockchain. Sort of what is the radical idea behind the blockchain? And it's actually first introduced in the Bitcoin white paper by a pseudonymous party or group of people called Satoshi Nakamoto. And their key insight was, well, if a central clearinghouse is a problem, why don't we replicate the clearinghouse and let everyone be the clearinghouse? So instead of trusting that role to one party, you trust it to literally everybody that wants to be a clearinghouse, right? So you have this completely decentralized payment network where anybody in the world can just run software on their computer that acts as a clearinghouse, collaboratively. And of course, now you've sort of made the problem worse in some sense, because now we have not one copy of the data, but we have hundreds, thousands of copies of the data. So we have this giant replicated database of who is owning how much money, or who is paying what money to whom, and we are replicating it all over. So we need to keep that in sync, right? And the blockchain is essentially a data structure, a distributed data structure, which is, you can think of it as a replicated database to which you can only append data, right? That's the idea, and I sort of highlight that here. So what is a blockchain? It is essentially a chain or list of blocks. Every block contains sort of a list of transactions. Each of these transactions is a node like this. Of course, I'm oversimplifying, but that's the bottom line, right? It's like Alice saying she wants to transfer a Bitcoin to Bob. It's stored in a transaction. Transactions are grouped into blocks, and blocks are linked with each other through what are called hash pointers, and I'll talk more about hash pointers in a minute. Okay. Now, of course, we've sort of shifted the problem now back to transaction order is still an issue. Now, within a block, okay, you can order transactions within a block, but then there's a question, how do the nodes agree on that this is actually block n+1, right? Like there might be multiple blocks n+1 that follow this block. And so there's this question of what block do you agree on as being the next block, and everybody has to agree on the same. That's where consensus comes in, which again, I'll talk about later. Okay, so that hopefully gives you a good view of where this whole blockchain idea came from. Now let's look a little bit at, the cryptographic building blocks, as I mentioned, okay? So how is cryptography used to securely record transactions on a blockchain network? So here I have just a very simple blockchain network, like 5 validators, and you see they have these pages with blocks, right? So there's the transactions, if you will. And so again, you can think of these blocks as essentially lists that contain information like, oh, Alice pays Bob $10, Bob pays Carol $10, and so on and so forth, okay? That's the essential information that is being recorded. And so Alice, in order to participate in this network and enter transactions into a block, what she needs to do is she starts off by generating a key pair, a public-private key pair. So that's one interesting thing about blockchain networks. You typically don't have some centralized PKI. Every user can generate as many identities for themselves as they want. And as in any asymmetric key crypto system, you have the public key that you can reveal to the outside world, the private key that you better keep very safe. And then in order to enter a transaction into that ledger, into that blockchain, what you have to do is you have to digitally sign the transaction. So you take the data, you take the private key as input, and your signing algorithm will generate a signature, which is just a blob of binary data that you just stick inside of that transaction object so that everybody can verify. So the verification, that is of course the job of these parties here, the validators. And so a validator can just takes, whenever it receives a block, the duty of the validator is to make sure that all of those transactions are legitimate. And in order to do that, they need to look at the data. They first need to verify the signature. So they look at the signature, they look at the data, of course, they take the public key of the party that is spending the funds. That's the important thing. It's Alice paying Bob, so it's Alice that should be signing that transaction. And then you get a yes or a no, like either this is good or not. And even if it's good, of course, there's other stuff that the validator needs to do, like checking if Alice actually has at least $10 in her bank account, right? So that's the other thing that they have to do. Now, interestingly, and I think Bart mentioned this on a couple of occasions in his talk on PKI, is he always talked about, so how do these companies that provide all of these security services, how do they actually make money? Nobody wants to pay for these things. You heard him say multiple times. And I think this is an interesting thing that blockchain somehow, I wouldn't say it got it right, but it provided for the first time an alternative system, which is that this whole system introduces a currency, because anyhow it's meant to do payments, and it uses the currency that it actually regulates as also a reward system. And so, for instance, and this is something that Bitcoin pioneered, but I think most blockchains took over that idea, which is how do you incentivize people to join this network, buy a big server, and actually do all of that signature checking and validation? And also, how do you make sure they do that honestly, right? So these guys have to have a vested interest in this network staying up to date, being fully secure, always available, and so on. That costs time, money, resources. How do you incentivize these people? Well, what did Bitcoin say? Well, anybody that verifies all the transactions in a block and creates the next block in the chain can reward themselves by actually including a special, what's called a coin-based transaction, which is basically saying the network pays Victor, the validator, $1 or $10, whatever. And so this is a way that you mint new money in this system. This is the way tokens enter circulation. And so it's used, this is both acting as the mint, right? Like normally the central bank can make money. Here, the network makes the money itself based on some algorithm. And it also acts as a reward system for these guys to contribute to the network, okay? So then the final thing, of course, is it's not just one block. There's these sequences of blocks. And as I said, order is super important in these networks. So you really have to make sure that there is some sort of strong relationship between these blocks. And so this is where cryptographic hash functions come into play, and these hash pointers that I mentioned earlier. What does blockchain do? Well, you take all of the content of a block, you pass it through a cryptographically secure hash function, so an irreversible collision-resistant hash function, and you get out some fingerprint, the hash, and you include that sort of in the next block. So or in other words, the next block has the hash of the previous block included in its body, and that creates sort of an immutable link between the blocks, right? So now you know, just by checking the hash and checking that it corresponds to this number that is included in the next block, you can check that these blocks are chained together, and so we have blocks in a chain, therefore blockchain, okay? All right, so if you look at the specific, if you're interested in, okay, so what public key algorithms they're using, what cryptographic functions they're using. So in the largest networks, Bitcoin, Ethereum, and so on, they use SHA-256, or in the case of Ethereum, they use Ketchak, which is actually a slightly different version to SHA-3, the algorithm that got standardized by NIST as SHA-3. Somehow, what I've been able to find is that the algorithm that got standardized as SHA-3 added 2 bits to the output of the message, and there was sort of the community was skeptical on why that late addition was made by the standard, and so the people working on, or the people that originally created these blockchain networks were very, very skeptical of anything that involved government, and therefore they decided, oh no, we're actually going to stick with the algorithm that was submitted to the NIST competition, which is the Ketchak algorithm. But the bottom line here is you have a cryptographic hash function that takes arbitrary length input string and a nonce, and you always get back this 256-bit hash, and it's collision resistant, meaning it is extremely difficult to find two different inputs that hash to the same value, and it's also hiding in the sense that from the hash you can't easily get back to the output. It's also, SHA is puzzle friendly, and that we'll get back to that when I explain proof of work. In terms of digital signatures, so the algorithm that is used to sign transactions in Bitcoin, Ethereum is the elliptic curve digital signatures. And here again, it's kind of interesting to see that Bitcoin chose to use a curve that is not standard. So they use the SIGP 256K1. Interestingly, it's also a curve that's fairly efficient to implement, up to 30% more efficient than other curves, I've been told, or I've read, because I'm not an expert there. But essentially, the bottom line is you have, in this crypto system, you have the public keys are 512 bits, the private keys are 256 bits, and the signatures are also 512 bits, okay? So that's the basic cryptography. Actually, there's nothing in the basic crypto of Bitcoin and Ethereum and most other networks. I guess for most cryptographers, this is boring. This is the boring, tried and true stuff, and I think that's actually what they wanted, to have the boring, tried and true stuff as the rock bottom on which to build. So these hash pointers, as I explained, this is where you simply take the hash, the whole hash of the previous block, and you store that as a data item in the next block, and so that hash acts as both a unique identifier for the previous block, and it acts as a secure digest, so you can easily tell if anybody goes back in time and tampers with the transaction data, all of these hash pointers break. So this is one of the key reasons why if you're wondering why are they using these hash pointers, well, it's so that every block actually commits to the whole past history, and if anybody tries to change even one bit in any prior transaction going all the way back to the original system, all of your hashes are different, and everybody can very quickly see that you are building on a different blockchain than the one that you're following. Okay, so that's essentially what I try to picture here. One change in the field here changes all the following hashes. Now, when I showed you earlier a block contains a list of transactions, that's not quite right. In fact, blocks contain trees of transactions, and this is using the Merkle trees that I believe, I don't know if you've covered them already yesterday, but I know that Bart mentioned them in his talk this morning. So the idea of a Merkle tree, so it's they're called like this because they were invented by cryptographer Ralph Merkle. Essentially, you take your data items, you hash the data items, and then pairwise, you take the concatenation of these hashes and you hash them again. You can take concatenation of the hashes, you hash them again, all the way up to until you get a single root hash that actually commits to the whole data set. So this gives you a number of benefits, and one of the biggest benefits is that a single hash commits to all of the transaction data at once, so it's very compact. And the other thing is that you can generate proofs of membership. And so the way this works is if I want to prove to you that this data item is part of this list of data items, then what I can do is I can generate what's called a Merkle proof. And the Merkle proof is essentially these three hashes here. So the hashes that are not on the path to the root, but on the sideway. And the way this would work is if I want to prove to you that this data item is indeed part of a tree that has this particular root hash, then all I need to do is give you these three green hashes, and what you can then do is you compute the hash of the data item, and with those three green hashes you can recompute the root hash, and then you can check if that root hash is the same as the root hash that I gave you as the root of the collection. And if those hashes match, then you have very, very high probability that indeed that data item is part of this larger collection, right? And as always, when we're seeing trees in computer science, you get this nice property that you only need a logarithmic number of hash items. So even for very large lists, you can verify that an item is present with only very few data items. So how does this relate to blockchain? Well, if you look at, for instance, the Bitcoin system, you have these transactions and they're all part of a block, but what's actually stored separately in the block is what's called the block header, and the block header consists of that previous hash, as I explained earlier, but also this root hash that commits to the whole transaction list, and then also a special number called the nonce, which has a different purpose, which I'll talk about when I talk about proof of work. And so the nice thing about this, why is this a nice property? Well, there is this thing in Bitcoin called SPV, Simplified Payment Verification. The basic idea is, let's say I have a mobile phone which doesn't have enough storage to store the whole blockchain. What you can actually do if you want to make sure that a certain transaction is valid, you want to make sure, let's say, is transaction one actually part of the blockchain? Then what you can do is you can ask the network, okay, send me only the block headers for what you believe is the longest chain. The block headers are very, very small, as you can see, it's just a few data items. So I can download only the block headers, and then I can ask, okay, now give me a Merkle proof that this TX1 is actually part of that particular block. Again, the Merkle proof is just a bunch of hashes, and so with very minimal data, you can actually corroborate whether that transaction object is indeed part of a particular block in the longest chain of the network. So that's how Merkle trees are used as part of blockchain systems. Okay, so I covered the origins, I covered the crypto building blocks. Now we're going to shift gears, and I'm going to take a step back and look at the system aspect of blockchain, namely, how does a blockchain network actually process payment transactions? Or in other words, what is the life of a blockchain transaction? What does that look like? So Again, a blockchain network, it's actually, in physicality, it's a peer-to-peer network. It's a bunch of computers interconnected with no central sort of routing node, if you will. And so you have users, and users concurrently submit all of these transactions. So in Bitcoin, they're like payment transactions. You have other types of blockchain networks where the transaction might mean something else. But I'm going to represent these transactions as these little squares. And so you can think of these squares as like the network being bombarded from all over the world with these transaction objects, okay? And so what we now need to do is we need to make sure that all of these nodes and all these validators, that they see the same set of transactions in the same order. So what these typically will do, these validators, when they receive these transactions from clients, is they will start broadcasting or forwarding them into the network. So this is typically using protocols called gossip protocols. So just like the way gossip and rumors spread in a social network of humans, you can devise algorithms that do a similar type of gossiping of information over the network. And so essentially every one of these validators ends up with this large pile of transactions, but they're not yet ordered. So that I draw them here in a Venn diagram. This is called the mempool, typically, in a blockchain network. So the mempool is this big bag of unordered transaction objects. And then one of these validators, a miner or a staking validator, depending again on the type of blockchain network, their role is to take this unordered set of transactions and to put them in a block, and putting them in a block means you assign an order to them. You say, okay, I'm going to take out these transactions out of the mempool, put them in a block, put them in a sequence, and then so now they have been ordered, the blocks, and now you again have a broadcasting phase, you again have a gossiping phase, but this time you're not gossiping a single transaction, you're gossiping around that block, and so that block gets disseminated over the network again, okay? And every validator, when they see such a block, they will check, okay, are all the transactions in the block valid? Does it actually follow the block that I thought was the previous block? And then they sort of add that to their local blockchain, okay? So, but of course, and this is the tricky bit, if this is happening in an uncoordinated fashion and any one of these nodes can at any time generate these pages in the book, how do you, what happens when you actually get like multiple people telling you, oh, this is the next block, no, this is the next block, okay? So you need to reach an agreement among the whole network about what the correct order is. That's called consensus, to make sure that everywhere in the network, everybody follows the same order, okay? And so I'll talk about consensus next, but just to wrap up the system overview. So the final thing that makes blockchain networks special is that they introduce tokens. And as I mentioned before, tokens are both the thing that the blockchain network regulates, it's the thing that in which you make your payment transactions, but it also acts as a reward system. That's really, really important. So this is a way to make sure that, yeah, somebody actually wants to participate in this network and keep it running. So tokens are, when they are used by users to broadcast transactions, they're typically called fees. And so typically what this means is when you pay with tokens, there's a small fraction of the tokens that will not go to whoever you are trying to pay, but that will actually be collected by the validators. So this is the payment fees. So because the argument is, okay, it's the users of the system that have to pay for the system. Who else would pay for it? And then there is that coin-based transaction that I mentioned earlier. So that's the incentive for these guys to actually keep the blockchain going, right? Through what is called mining or staking, depending on the blockchain. So then there is that big question is, who can actually be a validator? Who can actually join the network? And here there's two big models. So the model that Bitcoin, Ethereum, and many others follow is the open model, where there's essentially no gatekeepers. This is called a permissionless system because you don't need to ask for anyone's permission to download the software, run it on your computer, and connect to the network. There's, of course, places and situations where this is maybe less desirable, in particular in enterprise settings, where you say, okay, we are a group of companies, We are a consortium. Not everybody can be a member, but when you are a member, then you can join the party and you can be a validator. Okay, and so here's some examples. I'm guessing most people will recognize Bitcoin, Ethereum. There's many other types of permissionless networks that follow the same blueprint, essentially. And then we have permissioned blockchain networks. I believe Hyperledger Fabric is one that it's a system that was originally developed by IBM. They open sourced it. I hear it's on its way out again. It's no longer that well maintained. What many people tend to do these days, many enterprises, is to actually run Ethereum as a private network, which is actually makes sense if you think about your company intranet is also, it's not using a custom version of the HTTP protocol. It's just using HTML, HTTP in a closed setting, but it's using exactly the same technologies as the ones that are creating the open web. And we're seeing that in blockchain as well, where many people prefer to use the battle-tested tools of Ethereum inside of their company rather than using some esoteric other custom technology. All right, so let's talk about, so any questions so far? I'm always happy to take questions. All clear? Okay, all right. So let's talk about consensus, right? That's this problem of how do you make sure that everybody in the network follows the same blockchain, right? So again, a refresher, we have all of these transactions coming in from all over the place. We have each one of these nodes can potentially produce a block. So how do you make sure this happens in an orderly fashion? The problem is this: even with these hash pointers, if anybody can just produce a block at any point in time, then it's very easy to end up in a situation like this. This is called forks in the blockchain. So you have every block, of course, has just a single pointer to the previous block. But that doesn't stop you from generating two different blocks with maybe different transactions that both include a hash pointer to this block, right? So now you have these diverging histories. You have, this could be one version of history, but this is another version of history, and this is yet another version of history, okay? So which one should you take if you observe multiple such blocks coming in, okay? Because we don't want that. We actually want the network to stay together, follow the same blockchain. So what should we do? Well, maybe we can vote. We can ask everybody to vote, like, hey, I vote for this block, I vote for that block, and so on. Now, there's a problem. Well, before I get to the problem, let's first decide, okay, if we want to organize an election to elect who should be the party responsible for generating the next block, we need to organize a vote. And ideally, of course, and especially because, as I told you, every block generates rewards, right? There's new money in every block. You want to make sure that the chances of getting elected as being the next party is kind of random, right? That you can't bias the election in some way. But in a permissionless network, in particular, you don't even know who is part of the let's say, the list of candidates you can vote for, right? Anybody can spin up a new machine at any time. Anybody can go down at any time. So you don't even have a fixed list of nodes to organize a voting poll. And even if you would have like a list of all the nodes in the network, how would you assign your voting rights, right? So you could say, well, let's give every IP address one vote in the network. We could do that, okay? I guess I don't need to explain to you that generating new IP addresses is cheap. It's easy to do. You can rent them out from the cloud. So that makes it very easy for an attacker to control multiple IP addresses and rig the election in that way. And this is actually something, it's a pervasive problem, not just in blockchain, but in any kind of decentralized system. There's always this problem of what people refer to as a Sybil attack. And the problem of a Sybil attack is that you have the attacker pretending to be many, many identities, and because it's many identities, they can sort of be a majority, and they can push the system in a way that they prefer. And this is the same so I talk about IP addresses. You could say, well, maybe every public key is a unique identity, so let's assign a voting right to every public key. I'm sorry, but I can generate thousands of public keys on my machine right now. So that's the problem, right? As long as the resource you use to vote is not scarce, I can just mint however many I want. So maybe a better model in an open network would be not to do organize an election, but maybe we can organize a lottery, right? And in the sense that nodes can buy tickets, and whoever can prove that they have the lucky ticket is declared the winner, and the winner gets to propose the next block in the chain. But in order to do that, we need to make sure that our lottery has a few properties, just like a real-world lottery, by the way. You want the lottery to be fair, right? Meaning everybody should be able to buy tickets. You want it to be proportional, meaning just like with the lottery, you know, if you buy more than one ticket, if you buy multiple tickets, you expect that your chances of winning the lottery increase proportional to the amount of tickets you buy. And third, it should be verifiable, meaning if you declare, if you say, I'm the winner, everybody should be able to verify that you indeed hold the winning ticket. It should be very easy to verify the winner. So these are the three properties that you would want from a lottery. And indeed, this is what permissionless blockchains do, is they organize lotteries. The question then is, what do the tickets look like, right? Well, it depends. That's the answer. There's probably by now tens to hundreds of these lottery systems that have been implemented. The most widely known one for sure is proof of work. So proof of work is a system where you basically buy tickets by using compute power, right? The more compute power you have, the higher the chances you get elected to be the next block proposer. In systems like Ethereum, they use what's called proof of stake, and I'll say more about that later, but proof of stake means that you have to stake tokens, you have to lock up your tokens, you have to already hold some of the money, you have to lock it up, and the more money you lock up, the more you're invested in that system, and the higher your chances of becoming the next block proposer, right? And there's other examples, but essentially, as you can see, these things are scarce. I can only spend a token once, I can only spend a compute cycle once, right? And this is the thing that protects against the Sybil attacks. Like, you can't just spend your resources twice, okay? And so, so I show here these little blocks to indicate how much voting power every node has. And some may have a lot, some may have very little. And now, interestingly, the security of your blockchain network kind of depends on who owns these resources. And the key idea is now you have to sort of make this kind of weighted sum, because as long as a majority of the resources weighted by that scarce resource, as long as a weighted majority, if you will, is honest, is behaving according to the rules of the protocol, then the bad guys, right, the attackers, will not be able to break the security of the system or the properties of the system, okay? So this is, and this is essentially, it's both the strength and the weakness of blockchain networks, is that everything hinges on who controls the resources, right? So it can be very, very, very secure, but if somehow throughout time the resources, the distribution of resources shifts into the hands, where the majority shifts into the hands of the attacker, then the whole system kind of falls apart, because the attacker can always choose what the next block will be, therefore they can start censoring transactions, and you can basically halt the network, okay? The other thing, and this is what's sometimes called a 51% attack, I'm referring again to having 51% or more of the resources, is that you can double spend your tokens. So going back to my example with Alice, you know, remember I had this example of Alice sending a note to Bob saying, you can have my token, and then she creates another note and she sends it to Carol. Well, if you own the majority stake in the blockchain, what you can essentially do is you can pay someone, you let it be recorded in the blockchain, but then you create an alternative history of the blockchain that becomes longer than that original history, and you're basically rewriting history, and on that alternative version, you're paying Carol, you're not paying Bob. So you've actually effectively spent your money twice. So again, the moment you reach the 51% majority on the blockchain network, the whole system kind of breaks down. Okay, so let's talk a bit more about proof of work, which is the system that Bitcoin uses. So why is it called like that? Well, it's called like that because you have to do work to generate the next block. And this is intentional. Remember what I said, we don't want to see these forks, right? We don't want forking networks. We want everybody to follow nicely the same block. So why does Bitcoin use proof of work? It kind of acts like a delay, like a brake on the system where essentially you're slowing down block production so that creating a new block, you actually make it very hard, like computationally hard to create a valid block. And the way Bitcoin sets up the puzzle is that essentially it tries to make sure that new blocks only get produced on average every 10 minutes, right? If that goes faster, they increase the difficulty. If that goes slower, they decrease the difficulty. But you always get 10 minutes spaced apart. Now, 10 minutes is ample time for a new block to be propagated over the whole world, so over this whole wide area network, peer-to-peer, where you might have very, very slow nodes also. So 10 minutes should be more than enough time if somebody found a new block to disseminate that, so that by the time you create the next block, probably the majority of nodes have heard of the previous block, okay? So this is the purpose of proof of work, make it very difficult to create these blocks. How do they do that? Well, it's actually trivially simple. You take, in order to generate a valid block in Bitcoin, you take the block header, which includes the previous block header hash, the previous block hash, the root hash of the Merkle tree, and a special number called the nonce. And there's this equation where if you concatenate all of that and you hash the whole thing, then the hash has to be smaller than a certain target number. Or another way to say this is it has to start with a certain number of zeros. It's the same thing. And by adjusting that target, you can make this equation either very simple or very hard. Actually, because of the way the hashes work, it's very hard to predict ahead of time whether a certain whether a certain input will generate a valid hash. So the only way that you can be sure is you just hash the data, you get the hash, and you verify whether it's small enough. And so the nonce is there so that if you end up with a hash that is not small enough, what you can do is you can just change the nonce. Typically, what they will do is just increment it by 1. And if you know cryptographic hash functions, you know that even if you change just 1 bit of data in the input, you can get completely different output. That's the whole purpose of cryptographic hashes, of course. So what a miner does is they just increment that nonce all the time, you hash it, and every time you hash, you check that equation. And if you satisfy the equation, you have, congratulations, you have found a valid block. And then you want to broadcast that as quickly as possible to let the world know that you found a block, okay? So of course, this is purely probabilistic. So there's like, if you look at the probability to generate a new block based on the old block, there's a kind of probability distribution, but on average, again, depending on that target number, on average, in Bitcoin, it's configured to be every 10 minutes. And every 2016 blocks in the blockchain, there's an algorithm that will recompute based on the timestamps of the 2016 previous blocks. They will check, okay, what was the average time of the last 2016 blocks? And if that's below or above a certain target number, they will adjust. This is if you've heard of the difficulty, the block difficulty, that's this thing. So how then does proof of work actually solve our consensus problem? Well, the way it works is as follows. In Bitcoin, you have these miners and they're racing each other to find the next block. Whoever is first broadcasts it. And then all the honest nodes are configured to follow the longest blockchain. Meaning, if I see 2 different blocks that follow the same block, then I will wait a while, I will store both of them. And then when I see others mining on this chain and this chain becomes longer, then I will drop this chain. Then this chain is no longer the longest. And so I will just then, for instance, this miner in this configuration, when they are mining the next block, they will choose to mine it as a successor to this block and not to this block, okay? And remember that I said every block contains actually a hash pointer to the previous block, so you cannot concurrently mine on both chains because every block contains the hash pointer to the previous block, so you cannot wager your bets and mine on both chains at the same time. That's not going to work. Question? How do they bootstrap it? That's a great question. I think they bootstrapped it by, I think Hal Finney, who's also a very well-known cryptographer, was the first person to receive Bitcoin from Satoshi Nakamoto when he first published the system by just sharing the code on some cypherpunks mailing list, I believe it was. I don't remember the details. But essentially it was like bootstrapped in a tiny community, cryptographer community, the cypherpunks. And that's where more people started running some of these Bitcoin nodes. And I think the answer to your question is better answered by sociologists than by engineers, to be entirely honest. But it's a great question. Yeah? So it's the miner that actually has that mempool, so that unordered list of transactions, and it's the miner who gets to choose what transactions they will include in the block. They compute the whole Merkle tree, they compute the root hash, they compute the block header, and then by finding that nonce, once they found the nonce, they can generate this whole valid block, which contains the block header and the whole Merkle tree. Okay? All right. More questions, keep them coming, no problem. All right, so the corollary to this whole setup is that as long as the majority of the honest nodes as long as the honest node contains the majority of hash power or compute power, then a dishonest node or an attacker will not muster enough compute resources to sort of overtake the longest chain. That is what the whole security rests on. Now, proof of work is technically a brilliant solution to this particular problem, but of course, as people have quickly found out afterwards, it has a number of sort of by design flaws, if you will. For instance, it's pretty slow by design, right? Like, as I said, the whole purpose was to make block production difficult and to slow down block production. It's also extremely energy inefficient, again, by design, because you actually want nodes to spend computational effort. If that would be easy or free, then you would not buy any security with this system. But of course, and there is the problem of, okay, if it's energy inefficient and you're mining with fossil fuels or carbon-based energy, then of course you have the negative externality towards the climate and so on. That's one thing. The other thing is that, as people have found out, it's also subject to centralizing economies of scale. So an economy of scale is, in very simple terms, it's an economy where the more units you produce of a system, of a product, the cost per product goes down, right? And so, meaning if I'm artisanally creating units versus if I have a factory that automates production, I can make my product extremely cheap and I can outcompete the poor guy who has to make everything by hand. Well, it's the same thing in blockchain. In the early days, people had these mining rigs, which are a bunch of GPUs next to their desktop, and they were mining Bitcoin at home like this. Today, if you want to compete in this game, then, you need, first of all, you need ASICs, so special purpose circuits, which have the whole SHA-256 algorithm baked into the silicon. And second, you want to have many, many of them and put them in a place where energy is almost free and where cooling is not an issue. So for instance, a geothermal plant in Iceland would probably be some ideal thing. And this is actually happening. So you have these large-scale professional Bitcoin mining facilities. And so Bitcoin mining today is really a sort of completely industrialized economy. So that does create centralization. So people have tried other things. And I think probably by now, most blockchains, or let's say the second, third generation blockchains, have shifted to another type of consensus algorithm called proof of stake. In proof of stake, as I mentioned earlier, your chances of winning the lottery are proportional to the economic stake you have in the system. And the more tokens you stake, and stake meaning you lock them in some sort of escrow contract where you're no longer able to access those funds, the more you have locked away, the more your incentive is to protect the system, the more you have to lose also, so the more chances that you get elected. There's actually two types, going back to what I mentioned earlier with voting, doing a voting round versus holding a lottery. There's two types of proof of stake systems, so lottery-based and voting-based. The earliest ones were mostly lottery-based, and I think that the latest generation is more voting-based. So voting-based algorithms, they use fairly traditional distributed algorithms like BFT. BFT stands for Byzantine fault tolerant. So it's a type of algorithm where nodes get to vote in different rounds, in multiple rounds, and then you collect all the votes. And as long as you have a majority, actually a two-third majority, a super majority, you can be sure that the voting is correct, even if you have a number of malicious entities in the system that are actively trying to rig the system. So in these voting, actually, this was the next slide. So these voting-based consensus, there's two big families. One is called CFT, crash fault tolerant consensus, and the most famous algorithm there is called Paxos. It was invented by Leslie Lamport. He's a Turing Award winner, very famous person in the world of distributed systems. And then you have these BFT algorithms, or Byzantine fault tolerant algorithms, and the most well-known algorithm there is called PBFT. Was invented by Barbara Liskov and team at MIT, also Turing Award winner, by the way. So clearly, I mean, these algorithms were invented by very famous people, and they have very important functions. The key difference between these two schools, by the way, is crash fault tolerant, as the name implies, is tolerant to certain parties in your election system going down, crashing, but it cannot tolerate even a single one of these nodes cheating the system. So someone trying to actively rig the election. If you use a CFT algorithm to do your votes and there is even one malicious party, all bets are off. In a BFT system, you can tolerate, but the benefit is actually in a CFT system that up to half of the parties can crash and you can still continue. In a BFT algorithm, the trade-offs are different. You can only tolerate up to 1/3 of your members in your group failing, but you can tolerate also up to 1/3 of those nodes being cheaters or traitors, so people trying to rig the election. As long as 2/3 of the nodes are following the protocol, then even if 1/3 of the nodes is completely is doing any kind of deviation from the protocol, that's what people mean by Byzantine. It's a term that's used to describe an attacker that can do anything, right? So even if you have 1/3 of your nodes being Byzantine in a BFT algorithm, you can guarantee that the remaining 2/3 of the nodes will be able to continue to make progress, and everybody will vote on the same. The election will end up with a single outcome. So this PBFT algorithm, practical Byzantine fault tolerance, was invented in 1999. It was the first time. So BFT has been around in the academic community since the 80s, but it was always quite impractical until one of Barbara Liskov's PhD students wrote PBFT, which uses sort of sufficiently cheap cryptography. This was also back in the 90s when cryptography was still expensive, even on desktop computers. And so PBFT was fast enough that you could actually run it, but it was still sort of designed to, you would use it if you have a replicated database, for instance, and you want to tolerate like arbitrary misconfigurations, and maybe you run it with 3 nodes, with 5 nodes, maybe with 7 nodes. That was sort of what it was designed for. But with blockchains, we are talking about hundreds of nodes, thousands of nodes that are trying to reach consensus. So it did take a while for people to figure out how can we take this old algorithm PBFT and actually stick it into a blockchain. Probably one of the first ones that got it right I think is a person called Do Kwon, and he published this paper, I think this was 2014, so that's 6 years after Bitcoin. It's called Tendermint, and this is now the algorithm used in the Cosmos blockchains. If you've heard of those before, they use this. And I'm not going to go through the details here, but the bottom line is that Tendermint is essentially taking PBFT and adding it to a blockchain where you're sort of at any point in time. So first of all, what they do is you have to stake tokens, and then they take, let's say, the top 100 stakers, so the top 100 nodes with the most staked funds, and now you have a group of 100 nodes, and that is now you can start organizing an election in these 100 nodes, like who should be the next person to produce a block. And there is an algorithm that pseudo-randomly goes through every one of these 100 nodes, and they take turns producing a block. And when they produce a block, they have to go through these voting rounds where they say, okay, I have produced this block, can you please all check? And if you think that the block is valid, put your signature on it and give me back the signature. And then you wait until you get at least 2/3 of the signatures back. And then when you know that at least 2/3 of the nodes have signed the block, then the block becomes the next valid block, and you go on to the next epoch in the algorithm. So that's the bottom line. There's also Ethereum, which is, let's say, it has a very, very difficult algorithm. I don't think I'll have time to explain, but the bottom line is also that from the thousands of validators that make up Ethereum, in fact, I just checked this morning, we have over 1 million of these today, so over 1 million logical entities in the system that have staked money. There's a random number generator, sort of a random collective random number generator that sort of randomly draws from that pool one block proposer and a committee of at least 128 other nodes, and that committee will check whether the block created by the block proposer is valid, and if you have at least 2/3 of the signatures from that committee, then you can declare the block as valid. And there's lots of other details. You can have a look at the slides if you're interested. So permission blockchains, as I mentioned, they are taking the approach where you have a closed set. So and then things become a lot simpler. So for instance, Fabric is often used with only a handful of nodes, and then you can just use very traditional algorithms. Again, I'm not going to go over this, but because of this, there's very different trade-offs in terms of what you get out of a permissionless and a permission system. Okay, I'm gonna skip over this as well. Maybe the bottom line is, if you're really, really interested, this is more for PhD students, I think. If you want to know what is the state of the art in consensus, it is DAG-based consensus. And I put a few of the recent papers here that talk about, so DAG-based in the sense that you're no longer creating a linked list of blocks, but you're creating a directed acyclic graph of blocks, and it turns out you can get a lot higher throughput with these algorithms. But this is bleeding edge stuff. Blockchain beyond payments. So I think Bart already mentioned certificate transparency earlier today. It uses much of the same cryptographic primitives and building blocks, but it's not used for payments. It's used for transparency, like tamper-proof logging. You can have randomness beacons. This is what Ethereum also uses to create these pseudo-random elections. You can use a blockchain as a decentralized PKI, decentralized name registry, so DNS, but without root servers and these kind of things. So people have uncovered many new applications beyond the original payment case. All right, so I'm gonna wrap up, and I'm gonna just skip over to the final 2 slides. So blockchain is not a done deal yet. Privacy and scalability are 2 perennial issues of blockchain systems that are still being worked on, and also light clients. So the idea of, mobile phones are not strong enough to actually participate as a full node in these networks. How do you make sure that even if you're on a mobile phone, and you interact with this blockchain, that you get hard security guarantees. That if you're just talking to the wrong node, then of course all bets are off. You want to avoid that. Okay, so that was mostly it. We talked about the origins of blockchain, the cryptographic building blocks, how transactions are processed, the most important consensus algorithms, and then very briefly about permissioned and permissionless. Ethereum, if you're interested in the details, I have another talk that you can consult online that has more detail. And with that, I will wrap it up. So thanks a lot.